Hi, everyone. I'm Alicia Kinoshta, Associate Professor in Civil Engineering, and I'm working with Jack Mikesell, a graduate student in Civil Engineering at San Diego State University. Our team, Team Water, is part of the Connecting Wildlands and Communities project. And today we'll provide you an overview of our work leveraging models to inform watershed sustainability. The image on the left depicts the change in temperature in the Southwest. In the late 20th and early 21st centuries, the Southwest has experienced an unprecedented period of sustained high temperatures. While there are areas of higher moisture content around Southwest streams, this usually equates to higher wildlife abundance and diversity. Generally, ephemeral and intermittent streams make up about 81% of all the streams in the arid and semi-arid Southwest. This makes meeting domestic and agricultural demands a high priority for watershed sustainability and food security in the Southwest. Projected population growth also exacerbates these conditions and demands on our water resources. Examples of declines in water volume and storage are shown here on the right. Additionally, studies have noted that higher temperatures often lead to earlier spring warmings, earlier snowmelt, or decreased surface water and contribute to an increase in wildfires. Thus, consideration of the cumulative impacts from anthropogenic uses on these streams is critical in watershed-based assessments and land management decisions. So what is watershed sustainability? We can think about this broadly for a variety of contexts. Water supply sustainability is where we are concerned about having enough water in lakes and streams for the environment to perform ecosystem services. Water use sustainability is where we want to ensure there is enough water for society to enjoy aesthetically and recreationally. And stormwater sustainability are natural features and man-made infrastructure designed to mitigate flooding during rain events. To evaluate these metrics and watershed sustainability, we're studying the effects of vegetation and land management on water quality, erosion, and sedimentation to promote sustainable utilization and management of water resources and the environment. This approach will help us directly relate hydrological, environmental, societal, and planning conditions within a watershed. So let's consider each of our watershed sustainability metrics and evaluate what will impact it. The images on this slide are of Folsom Lake, on the left 2011 and on the right 2014, showing the stark differences between a normal and a drought year. This highlights the importance of thinking about how climate change, prolonged drought, and increased consumptive use can impact the sustainability of our water supply. In this image of the San Diego River, you'll notice trash, and some of the sources include illegal dumping and people experiencing homelessness. These types of issues lead us to consider how pollution of bodies of water impact recreational use and ecosystem function. Ultimately, we think about what is the sustainability of our water use. We can also generalize stormwater sustainability with two examples. Here, we see an example of erosion and sediment during a storm event on the left, and on the right, pollution draining to the Pacific Ocean. This leads us to plan for how increased urbanization and sedimentation impact our receiving waters, especially during rain events. And finally, in this slide, we see an example of flooding and water rescue. Previously pervious areas, which allowed infiltration or floodplains, are increasingly developed or urbanized. So we also need to consider how the impervious concrete impacts natural features and our man-made infrastructure so that we may mitigate flooding during rain events. So now I'll turn it over to Jack Mikesell so that he can talk more about the hydrologic modeling that we're doing.
The goal of this work is to inform policymaking decisions that cut across hydrologic boundaries by linking regional land surface, subsurface, and climate conditions in Southern California. First, we consider what needs and conditions link hydrologic and jurisdictional boundaries. This requires establishing baseline conditions in areas without or with limited hydrology data, preparing for variability in extreme conditions, and providing data to support climate change adaptation strategies. Hydrologic models can be used to inform watershed sustainability. Models can estimate the response to natural and man-made features to predict every raindrop's path of flow over land and in waterways. Models can also be used to predict water quantity and quality, such as flooding locations, what pollutants are washed off into waterways, and how water bodies grow and shrink during wet and dry weather. Models also provide an opportunity to incorporate potential changes such as climate, land cover, and management activities. We utilize an open source modeling platform supported by US EPA called Loading Simulation C++, or LSPC. The model provided hydrologic and hydraulic conditions such as stream flow and water quality. We utilize LSPC to understand watershed sustainability because it is a land use-based model, where the inputs are generated by land surface categories, making it ideal for assessing human impacts on the water cycle across large areas. This model is also used across Southern California in the development of receiving water permits, including WQIPs and TMDLs. Our modeling approach utilizes hydrologic response units, or HRUs, to group inputs by categories. We utilize layered spatial data sets to form unique groups of hydrologic classes to model hydrology. How do we decide which spatial data sets are used to develop HRUs? We consider the most significant characteristics in the impact of flow of water. These include land use and land cover, which can be used to represent the impervious surfaces that induce higher runoff rates and impede water from infiltrating through the soil. Slope, which governs how water runs off. For example, there's often greater runoff intensity for steeper slopes. And soil infiltration capacity, which is used to assess the drainage ability of the soil. Soils with better drainage capacity are more capable of infiltrating water into the groundwater table. The upcoming series of slides shows how model output time series can be used to assess watershed sustainability. First, modeling runoff and flows under existing land surface and climate conditions can help answer a series of questions. Which streams retain enough flow year-round to support aquatic habitat? Which streams have the highest variability between wet and dry seasons? And which streams have the available volume to support the most extreme wet and dry conditions under current projections? A great benefit of LSPC is the model's ability to simulate a dynamic landscape over several timescales. This allows for the simulation of known disturbances to the water cycle, like wildfire incidents, and the landscape's recovery to it. Wildfire prevalence and recovery can be used as a land cover input by designing land classes that imitate these conditions, like changes to vegetation cover, vegetation type, soil permeability, and erosion potential. This can help answer questions like, how do wildfires affect short and long-term stream flow and erosion patterns? And how do wildfires exacerbate existing water quality concerns? A better understanding of these questions is key to enacting sustainable watershed management practices. A vital element of this project is producing tools that can be used widespread across regional and hydrologic boundaries. One way we address this goal is through the development of interactive web displays, which can give stakeholders with less modeling experience better access to model results at the spatial and temporal scale, which will help their planning efforts the most. Delivery of these tools allows stakeholders to survey baseline hydrologic and land surface conditions in their respective HUC 12 and HUC 10 basins. This also allows users to examine baseline water quality data with respect to upstream and downstream conditions to see the impact of impoundments and land management practices in their respective basin. Furthermore, the entire model framework will be made available to stakeholders, allowing for the integration of regional calibration techniques with local knowledge, data, and expertise. While our work is focused in Southern California, this approach is applicable throughout the Southwest. Our work highlights how modeling processes can utilize common land surface and meteorological conditions using open source data and modeling platforms, and highlights the significance of end user accessibility, how the final product will be made available to stakeholders so that the inputs can be augmented using more precise local data and knowledge to better reflect conditions on the ground. This also allows for a dynamic modeling framework that can be updated to reflect how conditions have changed over time. Our goal is that these tools and techniques that we have presented can be easily accessible and transferable, and can be used to improve local and regional management for connecting wildlands and communities.